Hi, my name is Matt Holliday and welcome back to my class on Programming in Go. So in this section I want to talk about error handling. First I want to talk about how we can use the more advanced features of Go error handling to do a better job. Okay, and that really means instead of just making a string, can we do some other things with errors? And I'll show how we can do that. But the second part is more about a general concept of how Go approaches error handling compared to other languages and why it's a good model. In a lot of cases, an error is just a string. In a lot of programs, we just call a call like func.errorf, and we create a string value. Now that gets wrapped in some internal object in the standard library that represents an error, but it's not very sophisticated. It's a string, and we can print it out and look at it, and that's good for just debugging things. But sometimes we need to do a bit more. Okay? So we recognize that the error object is actually an interface. It's anything that has an error method. So we can create other concrete types that can represent this, right? You know, I've got, again, my PhysGig joke here, but we can create an object with an error message. It returns a string value from error, but it can have other data in it. And that's what I want to talk about now, is how can we create a more complicated error type to do more useful things. So I'm going to build out a custom error type. And this came from doing some wave file processing. So I'm going to create a wave error. Now, in order to define that, I'm going to create an enumerated type for the kinds of errors, the underlying things, and I'm going to use those as tags inside a struct. Okay, so my wave error type is a struct, and one of the things it has is the kind of error, and the kind of error comes from these tags over here. Okay, right, based on some enumerated type. Right? And I may also have some other value I can carry along, and we'll see how I can use that. Okay? Now, wave error is going to be an error because it's going to implement the error method. And in this case, it's a little more sophisticated because I've got different kinds of errors, and some of them may have an underlying error, or some of them may have this value that I'm going to use in different ways. And so my error method is actually a switch statement that looks at the different tags and does different things. Right? It could be a case where it's just a plain message. It could be a case where I use both of those values, or maybe just one of the values that's embedded in my error structure type, the concrete wave error, that represents an error, right? And I'm going to show you a couple of helper methods I built, right? And I'll explain why I have those. But one of them, each one of them actually takes a value of my type, adds some information to it, and returns a new value. So it's copying, right? And basically it depends on whether I want to stick one thing in it or two when I copy, right? Pretty straightforward. These are just methods. They're private methods on my type. I'm also going to define some error variables. And each of these variables is just an instance of my struct with a particular tag in it. Now, in the past, I didn't use to export the type or the variables. There wasn't any use. Right? I create the type, it becomes an error interface thing, which somebody prints out, but there wasn't any reason for them to look at the variables or the type. There is now, and I'll explain why in just a second. So now I'm exporting these variables, but how do I use them? So here's an example piece of code. I'm going to start decoding a header of a WAV file. So I start looking at my bytes, and if I don't have enough bytes, well, I can return one error, and I'm just returning, in this case, the variable. It doesn't have any other information other than, well, you don't have a header. But then I start trying to decode parts of it, right? And maybe I get an error that's a little more complicated. And what I'm doing here, it's an interesting technique. I'm taking my original error variable as a prototype. I'm modifying it by making a copy and putting into it particular details of this error in this spot. And then I return that new value. So my error variable doesn't change, which is good because I might need to use it somewhere else. But I'm returning a copy of it with particular details. Now, there's other ways I could do this. I could create a big constructor in line here. I think this is clearer. I think it helps understand, okay, exactly what I'm doing, right, is taking this kind of error prototype, giving it some information, and then returning it. So I think it's a neat paradigm. Why are we exporting the types and variables? Well, there's a new capability starting in Go 1.13. It's called wrapped errors. Okay. Now, the way you may commonly see that is in like func.errorf using a new format, %w, which says take this error and wrap it. So now what func.errorf is returning is a little more complicated. It's still an internal thing, but it allows us to chain these errors together. Okay, it's not just one big string with, and again, the way you see this typically is top level error, colon, second level error, colon, third level error. All right, but in many cases that's just a string. And the problem with having it just be a string is sometimes I need to ask the question, well, did I get an error of a particular kind? So I do some complicated logic, I get back an error, and then I do a string search to see if it has the words not found, and say, oh, I got a 404, let me deal with that, right? The problem is the string search method of looking at errors is fragile, right? Is there a better way? And the answer is yes. So the notion of wrapping errors takes us to this concept of an error chain. Because instead of just having a string where my wrapping notion is, well, thing, colon, thing, colon, thing, I now have a structure under the covers where my top level error actually has a reference to another error, which has a reference maybe to another error, the actual original error. Okay? And now I can walk this chain and do some things. And I'm going to show a couple examples. Now, the notion of wrapping errors means we can unwrap. And in fact, I can now take my custom error type and give it an unwrap method. And if it has that, then it's unwrappable. And we'll see that in action, right? Now, all I'm doing is returning the underlying error. It might be nil, in which case, the functions that deal with unwrapping errors will say, oh, well, it's nil. That means there wasn't any other error. I'm at the bottom of the chain. Okay, it's kind of like a list, a linked list, if you will, and I get to the end if it's nil. Right? So I don't have to do any thinking here. I can just return the embedded error. And I wrapped it in the case of, if I go back a couple slides, right here, I created a header read from error, and I wrapped the other error inside of it just by putting a reference to it in my error structure, into my concrete type that represents the error. Right? And so it became, one of these maybe. Right? The header read error is the top level, it wrapped this, and that might also wrap something else, some underlying problem beyond that, right? And again, so I can unwrap them. That brings us to a couple of useful utilities, and the first one is called errors.is. And again, this is new with Go 113. Okay? I want to know if a particular error is part of this error response. And again, in the past, I might have tried doing a string search, guessing what I think is going to be in the string produced by calling the error method. Again, that's fragile. Instead, what I can do is I can use errors.is to say, hey, does this error value show up in the chain? Okay, and it's based on a variable, which is why I exported the variables from my custom error type. Because now there's something you can actually use in a type of comparison. And is a fancy way of doing the comparison. It starts with whatever error you have, and it walks down the chain trying to see, is this error match the error in the chain? And if so, it will return true. So here's an example, right? If I have a decode wave file, and it needs to open a file, I gave it a file name, right? And if you look at the code in os.open, it returns a path error, but a path error can usually wrap an underlying problem, okay? So I probably have a chain of 3 errors. I have my top level error from the mywave file package, which is wrapping a path error, which is wrapping an actual underlying error. And the one I'm looking for here, for example, is os.errorPermission. Now, os.errorPermission is a variable of error type, okay? And I'm just saying, hey, is this error have one of those somewhere in the chain? Because that's a way of saying, well, this is that kind of error, right? The underlying cause of my failure was a permissions error. And maybe, for example, I want to log that for security reasons. So I look and say, hey, did I get a permissions error? Okay, deal with it. And we do that by using errors.is. Okay, it's a much safer way than trying to parse the string or do a string search in the string to see if certain words show up. Now I can take advantage of this, right, with my custom type. Because in addition to doing an unwrap method, I can add is to my custom error type. And what I'm doing is I'm saying, hey, you gave me this error. Is it me? And what it's going to be called on, okay, remember when we called error.is, we gave it a variable. So you can imagine that this is being called where the receiver is one of my error variables, like header missing. I can't remember what I called it. Header missing, or header read from error, or whatever. Okay, one of my error variables is the receiver. So this method is being called on one of my variables given some other error. Okay, is it the same error? Well, the first thing I've got to do is I'm going to use reflection. And again, I'm going to punt. I'll describe reflection a little bit later. But I'm asking first, is it my type of error? Is it a wave error? And if it is, that means I can go and get the tag and then say, okay, it's one of my wave errors. Does it have the same tag? And my logic is if the tag is the same, then it's that kind of error. The fact that it has a different underlying error or the fact that it has a different position value or something doesn't matter. I'm just going to say if it has the same tag, then it's that kind of error, right? And that's, I think, good logic. So I can not only provide the unwrap method, I can provide the is method on my custom type. And that allows people to go figure out, did a particular error happen without trying to guess at what string they should search for. Okay. Go has one other method. Okay. So is, again, it operated on a variable, not a type. Okay. As operates on a type, not a variable. And what it says is, can I go into the error chain and extract an error of this type? Okay. You can almost think of it as a kind of downcasting, right? Given an error, can I downcast it to an error of this type? Now, that error might not be the top level error. It might be in the chain. Okay. So if I look again at my decode wave file, right, it may return an error because it couldn't open the file. And I said os.open is going to return a path error. And the path error might wrap something else, but let's not go there. Okay. Path error in this case is not a variable. Path error is a type. If we go look at os.pathError, it's a structure, which has, among other things, the file name or the full file path and the underlying error. Okay. So if I'm using errors.as, what I'm actually saying is attempt to extract a path error from this error. Okay. And if it works, okay, so I have to give it a variable to copy into. I'm going to give it the address of an os.pathError that I've declared. Okay, so I pass that in here, and I pass in the error. And if it returns true, okay, that means my os.pathError actually has a path error data in it. So it was a path error in this chain, and the information of that path error has been copied to my local path error variable that I declared. It's been decoded into it. Great. And that means I can do something. For example, maybe I don't want to pass back the wrapping error. Maybe I just want to pass back the underlying error, or I want to do something else with it. Okay. So again, this is a way of finding the error by type rather than by name, where name was an error variable. So again, errors.is and errors.as help explain why now I actually not only have a custom error type, but I export the custom error type in the variables, because this gives people a powerful way to figure out what is the underlying error and doing it without using string comparisons. In the last 3 years, there's been some controversy about how Go does error handling. And there have been some suggestions about changing it, which didn't happen. So now I kind of want to explain why, okay? And it has to do with these, we keep writing if error not nil return error things. And some people find that obnoxious, okay? I think it's actually practical, and I want to explain why. So I want to break down errors into two kinds. And I'm going to start with what I call normal errors. And a normal error is an edge condition in your program caused by either something you got as input, right? You got input from a user of the program, or you got input by doing a network query and getting a response, or the external conditions the program is running in, like is the network available, are you out of memory, okay? Now, to my mind, these edge conditions, these error cases, They're things you should expect to happen as you write your program. If you're writing your program to use a network, then it's possible that the thing you're trying to talk to isn't there or the network isn't working at all. If you're dealing with files, it's possible that somebody's going to give you a file name that's mistyped, or the file's been moved, or the disk is out of space and you can't write any more to it. And these are perfectly reasonable things that you should deal with when you're writing programs that use files or networks or whatever. Okay? They're just part of your program logic. Now, here's an example from Open, and I've simplified this, but it shows how we do this, right? We go into Open, we try to open the file. If it doesn't work, we create an error type. Okay, in this case, path error is a type. Of course, it implements error, so it satisfies the error interface. And so that path error comes up here and gets returned as the error from the function. Okay, and so we return errors as values. They're just values getting returned from a function. You assign them to something, you check them, right? Just like this. All right, great. What's the other kind of error? Abnormal errors. And I'm going to put them all in one bucket. The abnormal errors are not edge conditions caused by other things. They're edge conditions caused by you, the programmer. They're your bugs in the program. Okay? And they're abnormal because we don't write programs to have bugs. Those are not foreseeable. Okay, I mean, obviously every program has some bugs, but we don't write a program with the knowledge of, oh, I'm going to have these bugs in it. Okay? And so an example of that is a nil pointer, or reading past the end of an array, and Go handles that by doing a panic, which normally crashes your program. Here's an example from the Go standard library, right? We're calculating the final checksum of like a secure hash, right? So we've processed all the bytes, and now we're doing this little check that says, well, there shouldn't be any more. And if there are, panic. Because if there are, we had like an off by one bug, okay? It has nothing to do with the bytes that were passed in. It's not the fault of the byte slice that we're processing. It's the fault of the logic that's doing the processing. Okay? That's an abnormal thing. And there's not really a way of handling that in the program other than go fix your bug, rebuild the bug, redeploy the, rebuild the program and deploy the program. Okay? There's no other way to handle that really. And I'm going to explain why here in a second. Okay? So hold on to your seats because I'm going to give you an idea that's one from experience, hard fought. Right? If your program has a logic bug, crash it. Fail hard, fail fast. Okay? Now I'll put a little asterisk next to that and say, unless it's a safety critical program, but people don't do safety critical software in Go for obvious reasons. Okay? So why take this approach? I'm going to give you 3 reasons. Pardon me if this slide is a little complicated, but I'm going to walk through all of these. So the first thing has to do with how we develop software. Okay? And this is, again, this is from hard experience. You have some bug in the program, you throw an exception, it gets logged, and the program goes on. Okay? Maybe the program just treats it like, okay, I'm going to respond with a 404 and log the exception. But the exception might have said, hey, I'm getting ready to destroy your database. Okay? When people test your program, they don't go looking through the log file to look for exceptions because the log file, frankly, is almost always unreadable in most programs I've worked with. Okay? But if your program crashes, the system testers are going to write you a bug report. And that means that bug gets surfaced earlier, looked at, and then somebody can say, oh my God, this is almost going to be a disaster if we don't fix this. Okay? The second one has to do with debugging. I've also worked in systems where you have different processes in a distributed system. So I send an RPC to a process, it has an exception, and what it does actually is it wraps up the exception and sends it in the response RPC back to me. Okay? That makes it hard to debug because what we'd like to do is get the evidence of the problem close in time and space to where the defect in the code was. Okay? Close in time meaning as soon as the defect happens, we want to get some evidence. And close in space, like ideally right in that function or very close to it, not in some other part of the program or even in another distributed process in our system. Now, both of these first 2 reasons are good, valid by themselves. But now I'm going to give you the biggest reason, and it's really serious. Okay? Because we typically use Go to build distributed systems. And in a distributed system, the easiest and safest failure to deal with is what we call a crash failure. The process just dies. It goes poof, it's gone. And in most well-designed distributed systems, that's okay, because typically you have more than one instance, and you have it behind a load balancer. And so, one goes away, the other ones can handle the traffic, the system will create another instance. Why is that better? Well, here are the alternatives. The alternatives, and what I mean by where I'm going with this, and maybe I should have said this already. If your program has a logic bug, it's corrupt. And maybe now it's in a corrupt state internally. Okay? If we let it run, the possibility is it's going to continue in that corrupt state and corrupt other things. Okay? It could turn into a zombie and simply consume resources, okay, and become part of a DOS attack eventually. Or it could start babbling bad messages on the network and corrupting the other processes. And that gets a cascading failure. Your whole system goes down. Okay? Been there, done that. Or it could silently corrupt your database as it continues until the problem is surfaced somewhere else bad enough that then something finally happens. But it's too late. Now your database is trashed. Shut the system down. Try to find a backup. Okay? If we don't have crash failures, we may end up with what's called a Byzantine failure. And I'm just going to say they're bad. There isn't time here to describe how bad, but Byzantine failures are very hard to deal with. Crash failures are safe and easy. So the best reason to just panic and die when your program becomes corrupt internally, meaning it has a logic bug, is that's the safest thing to do. Crash. Get out of the system. We'll pick up the pieces and look at it from a debugging perspective, and the rest of the system hopefully will continue on safely. When should we use panic? Right? We should use panic when our assumptions about our code are wrong. If we get a nil pointer error, we must have assumed that the pointer wasn't nil, and so we dereferenced it, and we were wrong. Okay, our assumption that the pointer wasn't nil was wrong. Okay, if we look at the other piece of code about doing the hash, the assumption was we've gone through all the bytes. Oops, there's a byte left over. How did that happen? It's an off by one bug. Okay, so we panic when our assumptions about our program are wrong. Great. Here's an example. A B tree is a complicated data structure often used to build databases. Okay, it's like a tree. It's got a bunch of rules, and I've listed them here just for the heck of it. Okay, if any of these rules don't apply, if they're not true before or after an operation on the B tree, then we've actually corrupted the B tree. It no longer operates or behaves the way a B tree is supposed to, and if we keep going down this road, we're going to end up with a corrupt database. And so my argument would be, if we detect these conditions as we're working in this B tree, we should panic. We don't get here because the user gave us bad data. We get here because our logic of processing the B tree made a mistake. Okay, it put the wrong thing in the wrong place, and now our data structure is corrupt because our program is simply wrong. So an alternative approach is exception handling. It was developed in the 60s, popularized in the 70s with the programming language Ada for safety critical systems. Now remember I said fail hard, fail fast is not a good strategy in a safety critical system. Instead we have this notion of what's called graceful degradation. And imagine I'm flying an airplane with two engines. One of them fails. I would like to continue flying on the other engine as long as I can. It's better than crashing, because in this case crashing means people get hurt. Okay? Now, ironically, people don't use exceptions building safety critical software. And the reason for that is what it does to the complexity of the software. Okay? We have a notion of measuring complexity, and there's a tool called cyclomatic complexity I'll talk about when I talk about linting. Okay? It just measures how many paths there are, say, in a function, how many different control paths or logic paths. When we add exceptions, we just balloon that number out of control. Okay? If I look at an ordinary function, maybe it has two return statements. So there's two ways to return from the function. But if I have exceptions, every line of code that's not a comment could throw an exception and take me out of my function. And analyzing those with static analysis tools turns out to be hard. All right? And if it's hard to do it with a tool, that means it's hard to do it as an individual person doing a code review. It's just hard to try to find all those invisible control paths looking at the source code because they're invisible. They're not written in the code really. Not much. All right? Now, in theory, Go doesn't have exception handling. In practice, it sort of does. I'm going to show you what it is, and then I'm going to tell you why not to do it. All right? We have panic. All right? There's also another thing called recover, where you can recover from a panic. And so I'm going to give you a very simple example of that. right? It's a little bit of code, and this thing is just going to print recover colon OMG, right? My main function calls ABC, ABC panics, and inside this defer, and the only place we can do recover is inside a defer, we have a call to recover. And if the call to recover returns a pointer that's not nil, that means it's capturing the results of a panic. Some piece of data, which in this case is just the string, came back and we're just going to print it, okay? So in a sense, we've done exception handling. Okay, the model here is probably closer to what in the C language was called set jump, and long jump, all right? But I'm not going to go there. What I really want to get at is, well, I have this little snarky comment. I'm printing out the results of capturing this panic in the recover block. What else can I do? And the answer is, in most cases, I don't know what I can safely do, okay? If I'm getting a panic, it's because my program has a logic bug and has entered a corrupt state. Well, for all I know, it's still in some corrupt state, but I don't really know at this point exactly what the corruption is. Okay, now, this might make sense, and there's a technique that's been used in safety critical programs. You enter some region where you can do a panic and a recover, and you start by doing a checkpoint of the program state. And that way, if you hit the panic and recover, you can actually return to a known state by taking that checkpoint and putting all the variables back in the program where they were. And people don't do it very often because the way I've described it, it's very expensive. It's kind of like in a database where you do a transaction and a rollback, which is actually kind of expensive, but it's part of the cost we assume in a database. In your program, it's harder because your entire program state is the transaction. Every variable, the stack, conceivably everything. It's very hard to know what that state is and put it back to a known good state. And if you don't, well, then you have the possibility that you don't really know where you are, okay? So there are a few uses of recover. It's actually used effectively sometimes in running unit tests, where I can actually run a test, and if the test creates a panic, I can capture the panic and produce an error message, perhaps in a better way than just crashing the whole unit test, or the whole set of unit tests, okay? That's not a bad use. I've seen one or two other uses that are okay, but in general, I would say calling recover is a code smell. It's just not a good thing to do. We do not want to bring the exception handling model of other languages into Go. Okay? Now, I want to finish this with a couple thoughts about better ways to handle errors. And the best single thing we can do about errors is just not to have them. Okay? An error represents an edge case in the program. And the more edge cases we have, the more complicated the program becomes, the more logic it needs, if then else statements and so on. Okay? Or we can try to do this very useful idea of defining the error cases out of existence where we can. That reduces the number of edge cases, it reduces the complexity of the program. And there's some examples, for example, built into Go. Did I just say that? Yeah. Okay. You know, it's okay to append to a nil slice. It's okay to read from a nil map. It's okay to take the length of an uninitialized string. If we think about other languages, in C, an uninitialized string is just a character pointer with random data. In Java, it's a pointer that probably is nil. Okay, that's safer. But in both cases, I've got to do some logic before I can calculate the length of a string to make sure I haven't blown myself up. Right? In Go, an uninitialized string is just the empty string, and if you ask for the length, you get 0 because that's very logical. And so I just removed a whole bunch of if statements from my program that would show up in other programs, in other languages. Okay? I've simplified things. I've reduced the edge cases. I've reduced the complexity. All right? I've handled the errors by simply defining them out of existence. Okay? That's one thing. The other one is about how to write a program. Now, this is the kind of very simple, logic that used to be written into introductory programming textbooks 40 years ago. And for whatever reason now, we don't go there. A lot of the modern textbooks, they're about this neat new language, these neat new language features, this neat new framework, or vague ideas like computational thinking. Great, but we also need to think about the practical aspects of building programs. So here are some rules that, again, are going to keep you out of trouble. Right? Every piece of data should start in a valid state. Every transformation should take data from a valid state to another valid state. And we should never accept any kind of input at face value. we should validate it. Let me start walking from the third one, okay? For the last 40 years, about half of the security problems on the internet have come from violating rule number 3. Some clever programmer said, oh, no one's ever going to type more 1,000 characters on the command line. So I'll create a buffer in my program, I'll make it 1,000 characters long, and I'll take the input string and just copy it to that buffer without checking it, because nobody's going to type 1,000 character string. And the buffer lives on the stack, and so the wily hacker figures, I can write this 1,200 byte string, smash the stack, and take over the program. Okay? Because the data wasn't validated on the way into the program. Right? Let's look at the first one. Every piece of data should start in a valid state. One of the worst system failures I've seen in my career started with an uninitialized pointer value, and because of the type of programming language it was a random value from the stack. At least in Go, if you have an uninitialized pointer, it's nil, and you'll get a nil panic, and that's pretty clean compared to what happened in this particular case I'm thinking of, where that random value on the stack actually caused a chain of errors that brought the whole system down. Okay. All right, that leaves us this middle piece, and I'm going to tell you the middle piece is hard. That's where the rubber meets the road. That's where practical programming skills, discipline of programming matter. You really have to stop and think about what's going on and what are you doing and how to deal with it. Okay? And most importantly, you need to avoid being clever. The clever guy is the one who said, nobody's going to write 1,000 characters into my buffer. I don't need to check the input. Okay? The clever programmer is the one who assumed, I don't need to make sure I set my pointer values to nil if the language doesn't initialize them to nil on its own. And there's a bunch of other things here. And I'll really get down to the last two. Never ignore errors. Again, how many C programs on the internet call some system call, don't check the error, and when it's wrong, then they start failing in weird ways. And the last one, of course, is just the absolute most important. I'm going to talk about this more. Test and test and test again. You can't test enough. Okay? So this is just the kind of basic logic that we need to think about when we write software. And if we do that, it's going to put us in a much better position. Okay? Why does this matter to Go? So there's a philosophy, and I pulled out a quote from Dave Cheney's blog about why we do this, right? And again, people think that this little section of programming, that's verbose, to have all these if, error not nil things. Okay? But Dave Cheney's point is, we handle errors, we don't just kick the can down the road. And I want to follow that with one other thing, and that is, what you get out of this is visibility, right? The logic in the program is explicit. It may be verbose, but it's explicit. It's right there in front of you. What are the control paths? What happens in an error? You'll see it. You'll see it when you look at the code and when you do a code review, right? As opposed to having it magically happen behind the scenes, right? So this notion of making the errors visible and handling them is why Go takes this approach and not the approach of exception handling. Okay, so that's a little bit more on error handling in Go. I talked about how we can make the error system a little more fancier by creating custom errors and providing some additional methods like unwrap and is. Okay, and then I talked a bit about the logic of why we do errors the way we do in Go and why Go prefers this type of error handling to exceptions.